until I can open it. So good morning. We continue with our discussion on the relation between the Frechet derivative and the partial derivatives. We have already explored it. We have said how from total derivatives or the Frechet derivative you can get hold of this partial derivatives. And then we also proved that if the function is differentiable from Rn to Rm, then all the partial derivatives do exist. Okay. So the existence of partial derivatives are guaranteed by the existence of the total derivative or the Frechet derivative. This is what we have proved. And we were looking at an example, and possibly let me start from there. So we take this example. We have partly looked at, or we have considered this in the last lecture towards the end. Define f of xy to be not equal to 0, whereas this is equal to 0. It is defined everywhere on R. Sorry, on R2. So f is now a map from defined everywhere. Now what we have shown is that we are examining this particular function closely at the point 0, 0. This is the point where we want to analyze it. Now you see that the partial derivatives, that is df by dx, which if you want you can call this d1. And we are interested in at the point 0, 0. So if you look at this function, see, then we are working along this line. This is the point 0, 0. This is the x-axis, the y-axis. So the variation is considered only along this line, and on this line we take y is equal to 0. So this is equal to we are taking y equal to 0, therefore this is equal to x cube by x square minus 0 because x not equal to 0, and then considering the limit of this as x tends to 0. So you are taking f of x okay. So this is this one, and this you can easily see that this is equal to 1. Similarly, we compute d2f at 0 0, which is equal to df by dy at 0 0, which is equal to f which is equal to 0. This is equal to 0. Therefore, hence, if f is differentiable at 0 0, then the linear transformation from R2 to R1 representing the is represented with respect to the standard variable, standard basis for R2 and R1 by the matrix one 0. That's in fact this is it, d1 d2. Now let us see whether this is under the assumption that if f is differentiable at 0 0, then the linear transformation from R2 to R1 is represented with respect to standard basis for R2 and R1 by this what is called a 1 by 2 matrix. So 1 by 2 matrix. So 1 by 2 matrix. Okay. Now, is this is the question that you have. Okay. Now let us estimate if it is so. If it is, then what you have is this. Limit then what you have, f at 0 plus x, 0 plus y minus a is the derivative, that is okay, I will write it, a acting over the vector x, y, this is equal to this. This is the error term, and zero. This is what you have. This is just the definition. This is your A, this is the H, or whatever you call as the increment. So here we are taking xy as the increment that you have. Okay. Now let us compute this. What is this? This is fxy minus f00. So this is actually, that is x square x cube minus this part is x. Okay. Now this, let us estimate this, and let us compute this. This is equal to x y square divided by therefore modulus of this is equal to this. Now this is your Rx. Now what we need is that mod Rxy divided by norm of, this is equal to what you have is that mod x y square divided by this is the Euclidean norm. That's equal to now you see that as x tends to 0, y tends to 0, see this is bounded. I mean this does not go to 0. Okay, that's quite easy to see. So we will show you this along this for take x equal to y equal to 1. Okay. Then you are looking at the problem, just computing this error. Take x equal to y. So this is the line x equal to y. Okay. Then what happens? Then the error term, that is rxy, this is norm of xy, this is equal to this is equal to x cube divided by square plus y square, x equal to y. So it is going to be 2 that's equal to what does this mean? And this does, therefore so this is not the derivative. Okay, this has to be having this particular property. So this is not the derivative. Okay, so the derivative does not exist. Not differentiable. Zero. So there is natural question that you ask, is it ever possible to use the properties of the partial derivatives if they exist to conclude that the function is totally differentiable? Now this particular question we will take up later. Okay. So that tells the function is at 0, 0 has its both the partial derivatives existing, but the function is not differentiable at 0, 0. Okay. The converse we have proved, that if it is differentiable at 0, 0, then the partial derivatives do exist. Now we carry out this further and then ask some more special cases. We prepare the ground, and eventually what we want to prove is this, that is, if f on a particular open set E of Rn has its derivative 0 everywhere, then the function is a constant function. Okay, I will make a remark for that, but before that we will do some preparatory work. So let us start working on the preparatory work. So let us look at the following example. Make some notations, fix certain notations which are useful. So we look at another example. So we take E to be equal to the interval AB R1 bounded interval. Let us start with the bounded interval. So there is no problem, it's an open set. Now we take gamma to be a map from okay, more specifically into some part of AB okay into E sorry let me use I here. So this is to R. Now the scenario is this. You have the interval AB of the real line, and then you have Rn, and then you have this is the real line again. So what you have is you are defining a function gamma from this to Rn. So this is what you have. Something like this. So this is this. Let us, without loss of generality, let me denote it by gamma. And now this is lying on some E. And from there you have a function what we designate by F. So F is from Rn to R. It's a real valued function defined on some open set in R. Now this is your interval I. Okay. So this is, if this point is T, then this is gamma T. And then what you have is that if you use this one, and this is f of gamma t. So as t varies, the point on gamma moves from one end to the other. So if you want to call this gamma A, this you call gamma B. Okay, right. Now we assume or we define, and f is defined from R1. Now we define G from by gt equal to AB. This is defined. We assume that gamma is differentiable and assume that gamma is a differentiable curve This is a differentiable curve in R. Therefore, now let us define, assume that the function f is also differentiable. Then this is the function g is the composition of gamma and f, and g is differentiable and we have seen that g derivative of t, this is a linear transformation from R1 to R1, which is obtained as f derivative at gamma t this is what we have. This is a linear transmission from R to Rn. This is a linear transformation from Rn to R. Okay, because the order is very important, and we know that g derivative is given by this. Okay, so this is a special case of, so this is a what you call the is it coming out from the chain rule. Now let me try to understand this. Okay. Now let us write this in detail. So what you have is the following. So let now we can write this in terms of the partial derivatives. And you take the standard basis for R, which is just 1. Okay, right? Therefore, what you get is this. Then you see that the f derivative see gamma derivative of t is, because gamma has components, say gamma 1, gamma 2, etc., gamma n. Therefore, gamma derivative of t, this is equal to the matrix, of course I'll because gamma is from these are the components of that. And then you also have f derivative this is equal to the matrix so this is taken as a n by 1 matrix. This is taken as 1 by n matrix. Therefore, what is it? Therefore, g derivative of t is equal to the product of these two, namely and that is essentially, that's equal to sigma I equal to 1 to n times gamma I derivative of t. Okay, so sort of usual function of function rule or the chain rule that we have used. So this is g derivative of t. Okay. Now this let us keep in our mind. Okay. Now here we also assume that mod gamma or gamma derivative we can possibly assume that the absolute value of gamma derivative is not equal to 0, so that in the dynamical scenario what you have is t is taken as the time variable. This is the space in which you are moving, so you have got time moving from A to B. As you move from A to B, you are moving along the curve gamma t in E. Okay. Now evaluate something corresponding to this. For instance, an example is a function that you can talk about is what you call the speed of this. The speed of this, I mean, that's an example. This function is, see, now you see that gamma derivative of t is that sort of getting a kind of information about the velocity. Okay, right? So these are the direction ratios of this particular vector. So this is gamma derivative. Now the speed of this can be considered as the absolute value, or not the absolute value, it's the norm of gamma derivative of t. If you consider gamma derivative of t as the velocity, okay, so take scenario, that is the interval AB is taken as a time interval. This is taken as a time interval. Then gamma is a map from depicting the movement of a particle along let us take R3 so that is more realistic. So this is a space along the curve gamma, gamma t, that is the image of this. Okay, so t belonging to, now this is contained in t. Now if the function is differentiable, then you get a differentiable curve. Okay, so if the smoothness is reflected on the path, of the path. Okay. Therefore, what do you get? What is gamma derivative?